let's have a look at another question here involving capacitance. X has a capacitance of 18 microfarad. X is charged so that one plate has a charge of 48 microcoulomb. X is then connected to an uncharged capacitor Y and a resistor via an open switch S. So here we notice the diagram with two resistors connected in a single circuit or a single loop circuit with a load resistor and an open switch. As long as the switch S is open, there is no current or charge flowing in the circuit. And since there is no charge flowing in the circuit, we can assume capacitor X to be holding its charge of 48 microcoulomb. Moving ahead, calculate in joules the energy stored in capacitor X with the switch open. As I've just explained, switch S is open, which means there is no current flowing. If there is no current flowing, there is no charge flowing in the entire circuit. So the capacitor X holds its entire charge of 48 microcoulomb. So energy in a capacitor, we can write the formula in three ways. We can write it as half Q square over C. We can write it as half CV square. We can write it as half Q into V. Since I know the value of charge Q to be 48 microcoulomb, the value of Q is 48 micro is 10 power minus 6, 10 power minus 6 coulomb. I know that the capacitance of capacitor X is 18 micro, which is 18 to 10 power minus 6 farad. I can use half Q square over C. And when I substitute and simplify, I get the value of energy to be 6.4 into 10 to the power of minus 5 joule in its SI unit. Moving on to the next part, the capacitance of Y is 12 microfarad. Now, X is 18 microfarad, Y is 12 microfarad. So these values of 18 and 12 microfarad are the values of capacitances of X and Y. Capacitance is the ability of a conductor to hold charges. And since X has a higher capacitance, even when switch S is closed, X will eventually hold a higher amount of charge. Please make note of that because that will be helpful in figuring out whether your answers are correct or wrong. When they're now told that the switch S is now closed and they're asking us to calculate the final charge on X and the final charge on Y. Here we have a simple question. Whenever the switch S is closed, capacitor X initially remains charged, fully charged in fact, holding a charge of 48 microcoulomb, whereas Y is uncharged. So the amount of charge withheld in X will slowly start flowing from X to Y, and this will keep on happening up until the exact point where the potential V across the capacitor Y will be exactly equal to the potential V across capacitance X. I'll repeat again. Potential difference is something that is very necessary or required for the flow of current or charges. Whenever 2 points have a potential difference, for example, if I assume 2 points as point A and point B, and if point at or potential at point A is lesser than that of potential at point B, or the potential at point A is greater than that of point B, in either of these cases, charges will flow either from A to B or B to A. The charges naturally choose to flow from a region of higher potential to a lower potential. Whenever the potential remains the same, as is the case for the potential across X and potential across Y, the charges will stop to flow. So we are going to assume that the potential across the charge or the capacitance X is Vx, while the charge is Qx. The potential across the capacitor Y is Vy, and the charge is Qy. Since Vx equal to Vy, and I know from the capacitance formula that C is equal to Q over V, rewritten V is equal to Q over C. I can write the relation between Qx and Qy as Qx divided by the capacitance of the capacitor X, which is how much? It is 18 microfarad is equal to Qy, which is equal to divided by the capacitance of Y, which is 12 microfarad. I also know for a fact, or we also know for a fact, that the total charge is nothing but the charge that was initially at capacitance or capacitor X, which is 48 microcoulomb. So here we have two unknowns and two equations, if we clearly notice. So by the rule of mathematics, we are supposed to get a solution. So substitute and simplify, or rewrite them as simultaneous equations and then resort to simplification. No matter how you do it, you're going to end up with Qx to be approximately 29 microfarad, and obviously Qy is correspondingly going to be 19 microfarad. Here it makes sense that Qx is greater than Qy because Cx is greater than Cy, and since capacitance is directly proportional to charge provided potential is a constant, the answer makes sense mathematically as well as logically. This is another method we can use to cross-check our answer. Now, calculate the final total energy in joules in X and Y. So again, we can use the same formula that we've written before, that energy stored is equal to half Q square over C. So energy stored in total is equal to energy stored in capacitor X plus energy stored in capacitor Y. Simplify, substitute, compute, you get the final answer to be 3.8 into 10 to the power of minus 5 joule. Moving on to the next and the last part of the question. Suggest why the answers to A and B part 2 are different. They are different, as we noticed that in part A we have the total energy to be 6.4 into 10 power minus 5 joules or 0.64 microjoules, whereas in part 2 it is 0.38 microjoules. Obviously, the initial energy stored in one capacitor was greater than the energy or the charge energy calculated when charge is distributed to two of them. We can attribute to this loss in capacitance or loss in energy, as the energy or the power dissipated through the load resistor. So heat dissipated through the load resistor. Load resistor. So this is one possible answer. Along with heat being dissipated through the load resistor, another possible answer could be the resistance or the resistivity of the connecting wires, which could also increase the overall resistance offered to the flow of charge or the flow of current, thereby increasing the amount of heat produced and thereby energy lost or dissipated. So these are two possible reasons why the overall energy found out in the second case is lesser, even though charge is equally distributed between or proportionally distributed between the two capacitors. Thank you.